So let's talk about current density in a wire. In the previous chapter on capacitance, if a wire was hooked up to a battery, or more specifically, if a capacitor was hooked up to a battery, there resulted in zero charges moving, right, eventually. In this chapter, however, slightly different. We won't have capacitors. We'll simply just have a wire, right? And let me just write a zoomed in view of this wire. Okay, it's hooked up to a battery with a potential, V. It has a plus and minus side, and that creates, effectively, quote-unquote, positive charges to flow that direction, and negative charges to flow this direction. Okay, in this chapter, 26, you'll see that the current is denoted by the flow of positive charges. And this is just by a convention. It's how the textbooks are written. I realize that the actual charges that are moving are the free electrons. So actually, it is the negative charges that are moving. But in the book, they say, and they talk about charges flowing from positive into negative. Okay, so that's the convention. It works out the same way, right? Positive flows around from plus to negative. It's the same as negative charges flowing from minus to plus. However, the convention is just what it is. It's weird. However, when it's connected to a battery, what happens in this zoomed in piece of the wire is that, well, the positive charges are repulsed or repelled from the left side to the right side, right? Around from plus into negative. Okay? And so they move from left to right. Thus, there is a tiny electric field generated at all points in the wire. Right? At all points, including in my zoomed in section here. Okay? So because of this electric field, and this is a steady electric field, it's not changing in magnitude in time, the charges in the wire move at more or less the same rate overall, right? And that's known as the drift velocity, right? In essence, they move a very tiny amount, and then they bump into their neighbor, right? Well, then they stop moving, and now their neighbor continues on to move a very tiny amount, right? But effectively, overall, on average, charges appear to move at some speed, the drift speed, okay, or drift velocity. Now, with that in mind, let's take a look at, let's take a look at the cross section for this wire. Okay, cross section A, and let's try and estimate the amount of charge, right, the total amount of charge in some span, which I'll call delta x. Okay, how many particles at any given time are inside that region? Okay, so charge Q, right, same magnitude as an electron, it's just positive, and it's moving with some speed v. Okay, so we want to find ultimately, well, that was a weird Q, the total charge. So I'll write that capital. What does this depend on? What does the total charge in this region depend on? Well, you would think there would be a Q in there, right? The magnitude of the charge. It also directly depends on the cross-sectional area of this wire, right? If it's a thicker wire, more charge will be in this region. So thus we write that as A, right? Not 1 over, that's inversely proportional, but just A. It's also directly dependent on the delta x, right? The length of that region along the wire. So A, delta x, and Q. And so right now, the units for Q total are pretty weird, right? The units for, Q are coulombs. That's what we want, right? However, we're multiplying by A, which is an area, and delta x, which is a distance. So this overall is a volume, right? You may have seen that coming. A times delta X, that's volume V. So the units are coulombs times meters cubed. That's not very intuitive. But this expression that I've drawn right here is just for one charge. We want the total charge. And so we have to get a little clever here. We have to multiply by the number of charges in this region. It's not just that one I've drawn there. There's a charge up there doing the same thing. There's a charge down here doing the same thing, right? Same thing up here. There's charges everywhere. And so we really should multiply by, well, some number or some coefficient. And in order to cancel out that volume, let me just write it as V. We need to multiply by the number of charges in that volume. Right? Thus, the meter cubed will cancel, and we'll only be talking about, I'll call this value lowercase n. We're only worried about the number of charges. So in Q. Right? I'll leave that in there. And this is our total charge in this region. Right? By the way, this lowercase n is known as the number density because it's literally the density of the number of charges. Okay? Now, this is the charge. What about when these charges are moving? That's a current. So let's effectively multiply this equation by 1 in a clever way. Let's divide both sides by the same thing, right? So Q over T, Q over delta T, that's a current charge per time. On the right side of this equation, which of these numerator variables are changing in time? Is it the number density, number of charges in that volume in a given time? Well, for a steady current, right, if it's not varying in time, the number of charges is pretty constant. Okay, that drift speed is constant for a steady current or a steady potential applying that current. So that's not changing. The magnitude of the charge Q, is that changing? No, right? That's still the elementary charge 1.602 times 10 to the minus 19 coulombs, right? That magnitude is not changing. The cross-sectional area of the pipe, let's make our life easy and say that's not changing, right? It's a uniform cross-section. This delta X, can that change? Well, let's rationalize that by saying, well, if this is the start of the wire and it's connected to a battery, that charge will move from the very left side, right here, in this direction. So over time, its delta X value is increasing. Thus, if multiple charges are doing that at the same time, they're sweeping out a total volume. Okay? So in essence, the speed will change. Right? So N Q A times V. Okay? And this should be put as a vector. Okay? That will change. And we call this the current. That's a vector. So it may look a little different, this NQAV, right? But it's the same as charge per time. Now, if that's simply the current, that's all well and good. However, the title or the slide is titled current density. Well, current density we get by taking I and dividing that by A. I'm just taking the A on the right side here and bringing it to the bottom. So I over A is equal to what's left over, NQ times V. And we call this the current density. Well, I guess it's not total now, it's just J. This is the current density J. J is just what is used. I know it doesn't really make sense, current density, capital J, I don't know, whatever. It's just the variable that's used. So, whoops, vector. That's the current density for a wire. It's simply NQV. Now, what if I ask, well, what's the current density through part of the wire? Or what if the charges aren't going straight quote unquote horizontally through the wire? What if they're going up at some angle? Right? What if they're going like that? What's the current density then? Well, if we draw our cross section, right, of A, that excuse me, that current only depends on the charges moving through the wire, not across the wire. So this velocity here still has components. It has a component like that and a component like that. I'll call that one V parallel and this one V perpendicular. Right? I called it parallel because the area vector points that direction. Okay? And so this V perpendicular, if that component does not affect the charge moving through that cross-section. And so to generalize this a little bit, let's write the current dotted with the area. Right? That's a way to generalize this. And so that's some angle theta. However, not only does the angle change, or can the angle change, also the area itself can change. The cross-section can change. What if we just wanted the current through a tiny section of that wire, right? Well, now that little vector we can call dA. That's some differential part of the cross-sectional area. And so if that charge is still moving at some angle, like that, it still has components. And so this is just another way to account for, well, what if the area is changing? Okay? So in this case, we multiply by, or dot it into dA and take the integral. Right? So up here, J, this is the current density. And on the bottom there, that's the completely generalized way to write the current. Okay? All right. Thanks for watching.